Nova Consulting Services. I'm also chair of the Reliability Working Group with ESIG. I'd like to welcome everyone to this ESIG webinar. For those of you who are not familiar with ESIG, we are a membership-based nonprofit organization, providing our members with objective information, resources, networking opportunities in support of clean energy and energy systems integrations decisions. We do this through workshops, tutorials, webinars, blogs, working groups, task force activities, and generally producing technical resource materials for people in the field. For those of you who are members, thanks for your support. It's what really makes these webinars possible. Using this opportunity, I would like to invite everyone to the upcoming fall technical workshop in Philadelphia. It's taking place the week of October 27th. As always, the workshop will host a mix of technical content with a special topic workshop focused on large loads integration on October 30th. Our workshops and monthly webinars are open to everyone. So please feel free to register anytime on the ESIG website. So that's www.esig.energy, or you can find us on various social media outlets like LinkedIn or YouTube or Facebook. Before we get going with the actual technical content, just a few logistical items. First, all the participants online will be muted for the entire webinar just to avoid unnecessary distractions. We will have a Q&A towards the end of this session, and there is a Slido for the session. You can go to slido.com and enter the code ESIG23, and I think Brooke is going to post this information in the chat. So you can go there and post your question and it can be voted on. And yeah, please go to the Slido and upvote the questions that you're most interested in or enter your own question. And we're planning to save, again, 10 to 15 minutes towards the end, and then wrap the meeting up around 5 o'clock or at 5 o'clock Eastern. An email link will be provided once the video file has been posted. We'll also plan to provide short responses to any questions that are not answered during the time of the webinar. So don't be afraid to ask your questions in Slido. Okay, with that, I'd like to go ahead and get to the introduction of our topic and speakers. So this webinar is going to highlight recent progress in the Phasor domain and EMT modeling of grid forming inverters. It will first introduce the latest WECC standard library Phasor domain grid forming models, which include REGFM A1, REGFM B1, REGFM C1, and REPCGFM C1, developed in collaboration with major grid forming OEMs and software vendors. These models have either already been integrated into or in the process of being integrated into leading commercial stability simulation tools, which include Siemens PSSE, GE PSLF, PowerWorld Simulator, PowerTech Labs, TSAT, and Dig Silent Power Factory. Key control functions described in these models will be discussed today. Second, the presentation will cover the development of generic EMT models of grid forming technologies along with behavior in positive sequence and negative sequence. Subsequently, a discussion on parameterization of generic models against black box OEM models will also be discussed. So about our speakers. So we have two speakers today. I will introduce them in the order at which they will speak. Dr. Wei Du is the Solar Subsector Manager and Staff Research Engineer at PNNL. He holds a joint appointment as a Research Associate Professor at Washington State University and serves as the Interim Co-Director of the PNNL Washington State University Advanced Grid Institute. His primary research areas include control design, modeling, and simulation of power systems with a high penetration of power electronics. Dr. Du is currently the principal investigator of multiple DOE projects that investigate the impacts of inverter-based resources on the stability of power systems. He also co-leads the modeling and simulation area of universal interoperability for grid-forming inverters, otherwise known as the UNIFI Consortium. In recent years, he leads the development of WECC standard library of grid-forming inverter models in close collaboration with inverter OEMs, software vendors, EPRI, and transmission planners and operators. These models would have been integrated into leading commercial power system stability simulation tools for both industry and academic use. Our second speaker is Deepak Ramasubramanian. He is a principal technical leader at EPRI. His work at EPRI includes development of new and improved mathematical models and processes for the large electric power system to represent the behavior of inverter interface generation sources and loads, and evaluation of and development of transmission planning criteria, including uncertainty of sources and loads. With that, I think we can jump straight to the presentation material. So Wei, if you want to join us and share your screen, please take us away.
So Dustin, can you see my screen? Everyone can see my screen?
I see it, yes.
Okay. Thank you very much, Dustin, for the introduction, and it's a great honor to be here and to co-present with my colleague Deepak on this work. So as Dustin introduced, I will cover the first part, is about the WECC standard library grid-forming inverter models. So let's first take a look at today's IBR models in today's commercial transient stability simulation tools. So I think people all in this group all know that grid following inverter is approximately like a current phasor, and the grid forming inverter is approximately more like a voltage phasor. But if you look at those IBR models in today's commercial transient stability simulation tools, there were already very well developed standard library grid following inverter models in those commercial tools like PSSC and the PSLF. I believe actually GE developed the first generic grid following inverter models for WECC, and EPRI has done a lot of work also to improving those generic grid following IBR models like those WECC, REC, and REPC models. So those are very well developed. But if you look at the grid forming inverter models, before we initiated this work, actually there were no grid forming inverter models in those tools. We think that was probably not good, because if we believe grid forming is very important in the future, but if no standard library models in those tools, that is probably not easy for industry to adopt this and deploy this technology. So that's why in the past 4 years, this big team, worked together on developing a few standard library grid forming inverter models. So this is funded by the UNIFI Consortium, and also we worked very closely with the grid forming manufacturers, software vendors, and planners. As shown in this picture, you can see the research institutes include PNNL and EPRI, inverter manufacturers including SMA, GE, Vernova, and Tesla, most recently Tesla Energy, and software vendors including all those commercial tools like PowerWord, PSLF, PSSC, and TSAT. And we work together at the WECC Modeling and Validation Subcommittee with also their members on developing those standard library models. These models represent the first generation of the WECC standard library grid forming models and have already been integrated into major commercial transient stability simulation tools. So this is a brief high-level introduction of the key functions of these grid forming models in those commercial tools. We have the REGFM A1 model, which represents the droop control, grid forming droop control. And REGFM B1 model represents grid forming virtual synchronous machine control. And REGFM C1 and its plant controller model represent grid forming hybrid control. So the development of this, as I mentioned, the development of these models received a lot of support from grid forming manufacturers. So for example, the A1 model received some support, suggestions from SMA, and the RHFM B1 model, GE Vernova actually provided a pretty good current limiting and follow right through control in this RHFM B1 model. And for this RHFM C1 and the REPC GFM C1 model, Tesla Energy was heavily involved in the full process of this model development. So it is pretty well validated against their actual device. And this slide just shows the availability of these models in those commercial tools. You can see we have 3 library grid forming inverter models, and they are available in commercial tools like PSSE, PSF, Power Simulator, and the Power Tech Labs and TSAT. And most recently, the Power Factory also joined in this effort. You are able to find those models in different versions of these tools. So you can see that each of these tools actually is used by almost thousands of organizations across the world. So it is pretty impactful work, and I'm very honored to represent the team to introduce this accomplishment. So because of limited time, I'm not going to talk too many details about the previous developed REGFM A1 and REGFM B1 model. Those 2 models were very well introduced in my previous seminar at the Unified Consortium. If you are interested in the details about REGFM A1 and the B1 model, you can go to the Unified Consortium YouTube channel and find the previous talk, and it covers the details of those 2 models. But for this presentation, I will mainly introduce the latest approved model, REGFM C1. So I will first talk about the inverter model, and then later talk about the plant controller model. So again, this model was developed in collaboration with Tesla Energy. Tesla Energy actually provided the core control algorithms to support the model development and also supporting the model validation. So here I just want to talk about the hybrid control. This model utilizes a hybrid approach. So what I mean by hybrid approach is that they implement both the grid forming and the grid following control inside one single inverter. So implement the grid forming control, grid following control inside one single inverter, and they work together and they do not switch between modes. So in normal operation, so in this phase domain, you can consider this single inverter behave as a voltage source behind the impedance in parallel with the current source. And then they dispatch the grid forming unit, this which is the virtual synchronous machine, the steady state P and Q to be 0, in the steady state, and the grid, but they provide a transient response. But this grid following branch or current source branch will provide a steady state P and Q response. And I will explain more details on why we designed this model designed this way in later slides. And this slide shows the control structure. The structure, as I mentioned, this control structure implements both grid forming and grid following inside one single inverter. So you can see at the inverter control layer, the grid following inverter will give you a current reference, and the grid forming control will give you a voltage reference. And with the terminal voltage and through this virtual impedance, or some people call it virtual admittance control, it will give you the current reference from the grid forming branch. And by adding this grid following current reference and grid forming current reference together, we can get total current reference, and then we can have a fast inner current loop to do the inner current control and then generate the gate signals. So this is how it works, and we also have a current limiting implemented at current reference for the per phase current limiting. So this is the overall control structure, how they implement both grid forming and grid following inside one single inverter. And in phase domain, because this presentation, I will mainly cover the phase domain models. So you can see that this is a grid forming is modeled as a voltage source behind the impedance in the phasor model. And this RS and the JX represent the virtual impedance. It doesn't represent the inverter actual impedance. It represents the virtual impedance using the control system. And then this current grid following is basically modeled as the current source, ideal current source, and they will be interfaced to the network solver. And then I will talk a little bit more details of the control block diagrams. Because of limited time, I will not explain all the details of the control blocks, but all the model specifications are already public available. You should be able to find them and read them in detail. But here is just high-level introduction. You can see that for this grid forming branch, this use a virtual synchronous machine model. It has a very typical grid forming voltage control, which is very similar to an exciter control of the synchronous machine. And also it has a virtual synchronous machine model, which has an inertia and damping term, which is very similar to a swing equation of synchronous machine. So that will generate the voltage magnitude and the phase angle. And the grid following branch is also a very typical grid following control. It just gave you the active and reactive current reference, and then there is a PQ priority current limiting. So this is very similar to the existing WECC grid following inverter model. And then there is a current limiting. As I mentioned, in the actual control, there is a fast inner current loop, and then there is a current limiting implementing the inner current loop. But in the phase domain model, we cannot model all those fast transients. So here we model them algebraically. So what I mean by that is that during the fault, we will reduce the current of both grid forming and grid following branches proportionally to make sure during the fault, the current stays at the maximum, the magnitude stays at the maximum, and the phase angle does not change compared to the case without current limiting. So in that way, we call it circular current limiting. So we implement it algebraically to do the fault current limiting. And this is a Planck control model. The Planck control model, because this is a new hybrid approach that requires 4 signals from the Planck controller. That's why we have to design develop a new Planck controller model for this REGFMC1 model. So this Planck controller actually sends 4 signals to the inverter model, including the voltage and frequency references and the P and the Q references. The voltage and the frequency references was sent to the grid forming branch by the Planck controller. The goal is to make sure their P and Q will dispatch to 0 in the steady state. And the P command and Q command was sent to the grid following branch so that can achieve the real power path and the reactive power path control and also voltage controller. So again, I will just quickly go through the block diagrams here. You can see that the Planck controller send the voltage and frequency signals to the grid forming branch so that in steady state, the grid forming branch output P and Q is 0. And the grid following branch, they have the Q command. We have the reactive power path, which is basically regulate the Q of this grid following branch. And also on top of that, you can have the voltage control that you can regulate the term POI voltage by regulating the Q of the grid following branch. So you can achieve the voltage control. And this is frequency control. Frequency or say the active power path, which is also to control the P command of this grid following branch. They measure the side frequency and then have the power frequency droop. You are able to change the P command of this grid following branch. So here it's very important. I like to talk about the validation because when we develop this model, we test them a lot, and also then we send this PSSE version of this REGFMC1 and REPCGFMC1 model back to the Tesla team. So they use this model to validate the model against their black box PSCAD model. They have done a lot of testing, validation. So being both the strong grade and the weak grade. So you can see in this, in the middle, we show the strong grade, the high SCR short circuit ratio equals 10 and the XR ratio equals 10. So this is represent strong grade. And the right side represent a weak grade, SCR equals to 1.5 and the XR ratio equals to 3. So they have done a lot of comparison between this PSSE version of REGFMC1 and REPCGFMC1 model. And here the green line represents Tesla's PSCAD model. You can see for this frequency step change, it matched pretty well in both strong grade and weak grade. This is the frequency step down, the same, still match pretty well. This is the voltage step up. You can see the response as expected. I will not explain all the details, but you can see they still match pretty well. And also we notice that in the strong grade and in the in the weak grade, their dynamic performances are different, which is reasonable, but we don't change the parameters. So that means it works in both strong grade and weak grade. Voltage step down still match pretty well. This is high impedance fault at the POI, so the voltage you can see drops to 0.5 per unit for 0.5 second. It still match pretty well in both strong grade and weak grade. And this is a voltage fault. The voltage drops to 0. So again, in strong grade and weak grade still match pretty well. So the important thing we learned from this exercise is that we believe that for grade forming, it works in both strong grade and the weak grade without the need to tune parameters. So at least for this study, we don't tune the parameters for our PSSE model, and the Tesla team didn't tune the parameter for their black box PSSE models. It just works in the strong grade and weak grade. You can see their dynamic performances are different, but they are stable. And also another very important thing we learned from this practice is that for grade forming, positive sequence phasor models can actually capture their dynamics for all the scenarios I presented, right, in the weak grade and strong grade for those various disturbances. You can see PSSE, this phasor domain 2, still match pretty well with the EMT model for this kind of transient stability simulations. And also, Tesla team actually did one step further. They provided some field test results against this REGFMC1 and REPCGFMC1 model. This is the field test results. So you can see we have the power reference change. So you can see blue line is the field data, and the red line is the REPC GFMC1 model data, right? They match pretty well for this P reference change. Also, Q reference change, you can see again, it still match pretty well. We don't see the major difference. You can see some error here, but you can see actually the error actually is less than 0.1%. So this is a voltage reference change. Again, it still match pretty well. You can see it looks like here is a major difference, but if you look at here, the error actually is still less than 1%, so which is very, very small. So the validation again, field data is still match pretty well. So here, I know I went very quickly, but here I like to talk about the fault rise through concept of this REGFMC1 and RPCGFMC1 model, because in the academia world, in the academic world, so current limiting and fault rise through control is still a very active research topic. Many different new controls are proposed to address this issue. But here I just like to talk about how this model, how this hybrid approach can handle this fault rise through and the current limiting control very easily. Because if you went through all the block diagrams, you will find that the grid forming branch is very typical synchronous machine control, right? And the grid following branch is very typical grid following control. And the current limiting is also very simple. But by combining them together and operate them in a smart way, you can do the fault rise through very easily. So first, let's review the critical clearing time of the synchronous machine. So people talk about the fault rise through control for inverter-based resources. But if you look at the synchronous machine, most of the time, synchronous machine cannot ride through long-term faults because synchronous machine has a critical clearing time, right? You can use this very simple equal error criteria to explain, right? When the fault lasts too long and your phase angle will lose synchronism to the grid. So if you implement a virtual synchronous machine in IBR model for inverter, you will probably have a very similar loss of synchronism mechanism because of this kind of equal error criterion. But there is a very smart way to avoid that critical clearing time. So what I'm showing here in this figure is a key reason for this REGFMC1 and REPCGFMC1 model, why it can rise through a long-term fault. The reason, as I already mentioned in my talk, that we reduce the mechanical torque or mechanical power, I'll say the power reference for this grid forming branch to 0. You can see that if I reduce this P0 to 0, that means this grid forming branch output 0P in the steady state. That means during the fault, your phase angle will not move too much. So the chance for the phase angle to lose synchronism to the grid is significantly reduced, right? So that's how it can improve the transient stability. But if you dispatch the P and Q for this grid forming branch to 0, you cannot provide the steady state P and Q power, right? That's not what you expect from the source. That's why they have the grid falling branch here to provide the P and Q in the steady state. So that's how it works. It's pretty simple, but it works pretty well. I like this approach. Again, this was not designed by me. It was designed by a smart engineer in Tesla Energy. Here, I just want to explain how it works. So here is the summary and the next step. So for this talk, I introduced the recently developed standard library grid forming inverter models, REGFM A1, B1, and C1, and their plant controller. And because I already introduced B1, A1, and B1 in a previous seminar, so this talk mainly talk about the details about the C1 model and their plant controller model. And from the study, I also show that grid forming works in both the strong grid and the weak grid without the need to tune the parameters. I think that is pretty important thing. This is very different from the grid following inverter models, right? And also for grid forming for this study, another very important message I like to deliver is that positive sequence phasor models actually can accurately capture their dynamics for transient stability simulation studies. This is also different from the grid following inverters models because we know that for grid following inverter models, under some scenario situations like very weak grid, phasor models have limitations. But for grid forming, looks like we don't have this issue. Of course, that doesn't mean that you can use phasor model to test all kind of the different scenarios. And my colleague Deepak, he will talk more details about when you should use EMT models to do some studies. But here I like to emphasize at for those typical transient stability simulations, I think we should be confident of using phasor models for grid forming inverters. And also the next step is that it's very important to mention that the talk for those A1, B1, C1 models, they mainly represent energy storage systems because we do not model the DC side dynamics, and therefore we don't think we don't know if they can adequately represent grid forming solar or wind, or not. And we are still working on that, and hopefully we can have a better understanding of whether these models can represent grid forming solar and wind, and maybe propose necessary improvements. And also, as I mentioned, that the second is that current limiting and fault rise-through is still a very active research topics. These models described some fault rise-through concepts provided by some major manufacturers, like GE provided one in REGFM B1 model, and Tesla provided one in the REGFM C1 model. But overall, this is still the research topic, I believe, and more research efforts are needed to better understand what that means when you use different fault rise-through controls for the power system stability. And also another very important thing is that to develop guideline for developing positive sequence phasor models for grid forming inverters. I think this is also very important because people may think developing phasor model is pretty easy, right? Once you see the block diagrams, you know how to develop that. Actually, it's not that easy because in phasor models, phasor domain models, you have to be smart and analyze the model, understand in detail, and you have to make reasonable assumptions because you cannot model all those fast transients in the phasor domain model. We have to make reasonable assumptions and then to model them appropriately, and also make sure that this model can reflect the necessary dynamics. So I think some guideline is really needed how to develop the phasor domain models for grid forming inverters. And also the last one is a very important one is that we developed the first generation of those models. A1, B1, C1, but these models will always be updated on a regular basis. And we really welcome all the grid forming manufacturers to be actively involved in the model development. As you can see that the more the manufacturer is involved in the model development, the better these models can represent some commercial products and will be very meaningful and helpful for industry. Okay, so that's my talk. Thank you, I will stop.
Yeah, thanks, Wei. So I'll continue and talk a little bit about some of the work associated with parameterization of these models, looking at how do they really stand up against maybe black box models and variation of configurations that various OEMs might have with respect to their grid forming strategy. And then we'll also look at some industry applications of these generic models and also talk a little bit about an EMT domain representation of it. Before we go further, we also have to talk a little bit about some additional features that are available in various published generic models, especially being able to represent different kinds of control functionality within the same control model, within the same loop, so that transmission planners who want to play around and explore different kinds of performance requirements and functionality can do so at ease without having to switch out the model, without having to create a new case, without having to actually reparameterize and so on. We also talk about some features that were in our work at EPRI, we saw were required around the world, and they will make their way into the versions of the WECC generic models in subsequent versions and iterations as the need arises. But we saw aspects associated with requiring, say, something like a transient limit versus a steady state limit, some kind of prioritization of current during current limited operation, and requiring that for different kinds of grid forming modes, whether it is a PLL-based mode, whether it is a group-based mode, whether it's a virtual synchronous machine-based mode, and so on, and just seeing how it, say in this example, compares against an OEM model that comes about. We also found that few OEMs offer features in different parts of the world that have some kind of a rate of change of quantity-based response. So something like within the group mode, but still having a rate of change of frequency-based function that they put into their response, a rate of change of voltage-based function that they put into their response. And this is also required as a concept in some international grid code. So there are models available for use that can be used for evaluating different kinds of functionality that go beyond some of the standard library models and will sometime maybe merge with the standard library models as things go along. But that's how the generic model space keeps evolving. There are always some models available that might be a little bit, have more features available that then finally merge with the standard library models as more usage of it becomes prominent. But that being said, any generic model comes with the question of how do you parameterize it? And is the parameterization appropriate? Is it representative enough of the black box model that one is using? And how do we make sense of the ability of the model to represent the necessary dynamic behavior? We've all gotten used to looking at time domain traces, time domain responses that will, say, look at different kinds of changes in a single machine infinite bus scenario and see how the model response compares. And that's a very powerful way of identifying the performance of the generic model. But they may not always show the behavior for different kinds of frequency responses, different kinds of frequency spectrum analysis. So we've gone down that route now of looking at parameterization of these generic models from a frequency domain criteria perspective. So here is one example of how the generic model in positive sequence compares against an OEM model in their grid forming functionality.
Deepak, are you there?
Yeah, Deepak, we lost your audio. Still nothing. Sorry, folks, please bear with us a moment.
Hey, can you hear me, Dustin?
Yes, can hear you now.
Yeah, I don't know. WebEx audio kicked me out of the phone calls. But anyway, let's continue. So we've been looking at this, as I said, from a frequency domain perspective, and you see the positive sequence impedance as portrayed by the positive sequence model and the EMT model of the generic model. So the matches quite well with the OEM model. We see two other transfer functions. So active power versus omega, reactive power versus voltage, angle versus active power. They all track well across the frequency range. And some of these transfer functions are actually now being asked in different kinds of grid codes to help define forming behavior. So being able to verify that a generic model parameterization aligns with some of the OEM black box models can be very reassuring to get a sense of confidence in the generic model's behavior. And we see here the admittance, the 2x2 admittance of the generic positive sequence model compared against the admittance of the EMT domain model. Overall, the parameterization looks well. There is an angle wrapping that occurs here, but that's largely okay. But there may be some challenges around this 10 Hertz frequency range, but that is at the extreme end of the bandwidth of the positive sequence environment. So we do have to keep that into consideration when deciding to use the generic model versus using the positive sequence environment. Now, the question came up, and I think I saw a question in Slido also, how does this compare against different kinds of configurations that OEMs might have? So we took the same OEM and we looked at their non-grid forming model. So their non-grid forming EMT model, this is a parameterization of another positive sequence generic model in non-grid forming mode. And we compare against the different transfer functions. And again, overall, the non-grid forming positive sequence generic model seems to have roughly a similar parameterization or a good parameterization with the EMT model of the OEM, the black box model, and is able to capture multiple frequencies of oscillation that might occur. Here again, there is some amount of caution one needs to have at the 10 Hertz bandwidth mark of the software, but overall it is roughly good. Now, why I brought up this non-grid forming model of the OEM here is that this particular OEM in question has an option in their parameterization of their non-grid forming model. So here, the use of forming and non-grid forming for this OEM is based upon marketing terminology. That how do they market their product? So this particular OEM has a parameterization of their non-grid forming model that can actually pass the loss of last synchronous machine test quite successfully. So which means that the OEM has potentially two different configurations available to do or carry out this grid forming behavior and provide that to the system and provide that as a customer. So now the question is, can the same positive sequence model be used for characterizing both these configurations of this OEM from their black box model, or would different models have to be used when we are characterizing the OEM's response across the different configurations? So we'll get to that in a minute, but this aspect that the non-grid forming model of the OEM can actually showcase a performance that passes this loss of last synchronous machine test, which is very popular now in a variety of different grid codes, leads us to pause a bit and ask the following question, which I strongly recommend that each of you, when you are talking with your peers, when you're talking with your customers, your clients, your different OEM vendors, and so on, when you're presented with the concept of all existing inverters and following our current sources, maybe make it a practice to immediately ask, what is the control objective used to determine the current reference? And what is the expected response of that current source to step changes in grid voltage and frequency? And the reason why I say that is because this aspect of this OEM's non-grid forming model being able to survive loss of last synchronous machine implies that there is a parameterization of the non-grid forming model of the OEM that results in grid forming properties and behavior coming out. And that essentially means that there can be both an explicit voltage source representation and an apparent voltage source representation that could help improve systems reliability. But that was a kind of a tangent. There are other material available on this. But let's get back to the topic of parameterization of the model. What we found out was that at lower frequency, it might be okay. So there are a few graphs here. The OEM grid-forming model as the black box model, the OEM non-grid-forming model, which does not have grid-forming property, but the OEM non-grid-forming model, which can be parameterized to show grid-forming property, all in EMT domain is the solid curve, and the positive sequence model is the dashed curve, the generic model. So while in lower frequency, there might be a reasonably good representation of the behavior of using one positive sequence model for different configurations of OEM models as the frequency starts increasing. And here in this case, previously it was closer to 10 hertz where there was a difference. Now in this case, there can sometimes be a difference at 2 or 3 hertz also, which needs to be investigated. It doesn't mean that the model is not correct. It doesn't mean that the model is not appropriate. It needs to be investigated with further insight. So as one is looking towards more use of these generic models with different kinds of parameterization to represent different kinds of OEM behavior, to represent different kinds of black box model configurations, whether the same positive sequence model can be used or not may require a little bit more insight, may require a little bit more of such validation exercises that go beyond time domain, that go into frequency domain, to actually get a sense of guarantee on whether the parameterization is appropriate or not. If they are parameterized, the generic model is agnostic to control structure of a particular OEM, but if they are parameterized appropriately, they do represent the majority of characteristics and trends. Now note that we're not talking about detailed fault right-through behavior. We're not talking about detailed oscillation mitigation control and things like that. We're talking about the general trend of response that can be used when a system operator wants to plan their performance requirements, or when they want to get representation of a performance of a device that is farther away from the fault rather than being near the fault. Different flavors of generic models exist over and above what might be the traditional generic models that we have. And all of these generic models, both for GFM and for non-GFM, if they are parameterized appropriately, they can provide a whole variety of response. So if you want to learn more about how we did some of this parameterization validation checks and looking at the various different frequency domain traces and so on across multiple frequencies, feel free to reach out and we'll be happy to share more information on that. But now switching gears a little bit more, we spoke about positive sequence generic models and parameterization. Let's quickly talk a little bit about EMT generic models for grid forming technology. So we've been working with the team, both here at EPRI, collaborating with PNNL, with Unify, and so on, to look at different kinds of EMT models for grid forming behavior and different functionality embedded within the model. So looking at things like having different loops of control, looking at different fault right-through techniques, different fault right-through mechanisms, and different negative sequence control topologies and structures that might be implemented or might be useful for looking at these different devices. As I said, one needs to be careful about using these models, especially if you are looking at operation near the limit. There was a question, I think, that talked about phase jump power and how would the model be representative of phase jump power. That's one thing that we have sometimes found out with these generic models and OEM models, is that if it is operating closer to the current limit and there is a phase jump that occurs, one might have to look into this a little bit more to get an understanding of if the current limits are implemented in an appropriate manner for those phase jump responses. But the EMT model that we have been looking at this for both battery energy storage systems and eStatComs. And now we have some ongoing work looking at wind and HVDC also to look at the development of these generic models. But largely, they do seem to be tracking a little bit with OEM model response again. One thing to keep in mind here is be aware of transient current limits that certain OEMs might have and might be important to capture in the generic model. This is a response for a phase step of 20 degrees at a low SPR. And this is a response for a single line to ground fault. And here the aim was to try to track if the negative sequence current provided by the generic model roughly aligns with the negative sequence current that the OEM model provides. There's a lot more, of course, comparison results that can be done here. It's not to say that only a selected subset of comparison results are to be looked into. But overall, we do see that there are good tracking of performance of these models. And these models have had a variety of uses. We've been doing few application studies with various members here at EPRI to look at the application of not only positive sequence generic models, that's a different presentation that we can share, but looking at EMT generic model application. And one such study that we looked at was evaluating the capability for an inverter-based resource to be a black start unit. So essentially try to understand if you have grid forming capability in either a solar plant or a battery, can it really provide black start support services? Can it really provide energization of transformers and understand what changes might be needed in the energization process itself if an inverter is being used to carry out the energization of the transformer? Do you need to carry out soft energization? Do you need to carry out controlled energization? Do you need to look at inrush resistors to be put into place so that you can lower down the inrush current, and different kinds of aspects related to that. We were also looking at design criteria. Can the inverter-based resource provide negative sequence current to take care of sympathetic inrush that occurs when a neighboring transformer or a parallel transformer is switched in? And that leads towards determining design criteria for the inverter-based resource, which is going to be a black start resource. So the generic model helps in designing those bounds for the various performance requirements that one might need. So here was how we did soft energization with the inverter model for black start. We did this also as controlled energization, wherein you close the breaker at a lower voltage and get a smoother response. We've also been looking at the use of these generic models in EMT domain to look at the interaction with large loads. A lot of focus is now coming on large loads with a variety of different large loads that are coming into the picture. And here we looked at a large load that was there at a site location. The limited grid connection was one of the things that the customer wanted to look into. And then we looked at what happens if you have both wind and solar and a battery energy storage with grid forming capability in place, and looked at a combination of disturbances to essentially understand what should be the design criteria if it can be developed for these kinds of resources, for these kinds of facilities, for these kinds of plants. And that's where the generic model again comes into play. We looked at how much is the largest loss that the system can tolerate. We identified that the transient overload capability is going to become extremely crucial depending upon vendor to vendor, and that is something that the generic model helps provide visibility into. We also identified that maybe sometimes some kind of a protection mechanism could help even more large load loss that can occur within the facility, and identify what is the thresholds of fast load shedding that might be needed. We also wanted to identify within this facility what is the smallest size of grid forming battery that might be required. And we broke it down into whether it needs to take care of only the supporting role for small signal kind of events, or does it also need to cater to contingency events with respect to faults and so on. And we found out that if the primary role is only grid formation, then a smaller capacity is sufficient in this particular facility. So just to close out, we've had variety of generic models that have been developed that are available for use in the industry, both positive sequence and EMT domain. Of course, none of these models are complete. There are various flavors of these models. Some of them are in the standard library. Some of them are user-defined models with more features available in them. Some of them are features that will evolve over time. So as more learnings are obtained, these models would be refined and improved. But they can be parameterized. Any of these generic models, they can be parameterized to represent OEM's behavior, but they may not be able to represent every configuration of an OEM or every OEM, because that's not their job. The generic model is supposed to be vendor agnostic, it is supposed to be control structure agnostic, and it should be able to represent the trend of response over a large variety of structures. The idea is to know when to apply them for what frequency are they applicable, for what kind of studies are they applicable, is the parameterization appropriate? And as we showed some of the results in the earlier slides, there are now techniques available to help determine whether the parameterization is appropriate, whether the model is applicable or not. And we have seen preliminary application studies have shown promise, especially in identifying robust stability methods that could be applied for different kinds of models. So I'll close out by just highlighting that whole variety of members here in our EPRI team that actually help with a lot of this work and provide support on a variety of our work that we're doing here on grid forming. And with that, Dustin, I think we'll have some time for questions.
Okay, great. Thank you, Deepak, and thank you, Wei. Got a list of questions here. I'm starting from the top on Slido, and I'll read the questions out to you. I think you have them in front of you, but I guess the first one's hopefully quick. Will the slides be shared? I think this webinar, I believe, will be publicly available. But maybe Brooke can comment further on this. The slides will be also available.
Yes, the presentation recording and the slides will be available on the ESIG website.
Great, thank you. Okay, the next question from Eric Lewis says, in SOE, grid forming inverters have no control actions after a phase jump to allow the flow of phase jump power. When will you have this model available?
I can maybe take that as the first. So I think almost all the generic grid forming models that are there, the three models that Wei spoke about, REGFM A1, B1, C1, the GNR GFM model that I spoke about, and even the EMT model, they all have the ability to provide that kind of a phase jump power. When a phase jump occurs, we even had that slide in presentation here that I showed the EMT model's response to phase jump. Now, if there might be a few nuances there with respect to the specific type of phase jump power, if that is needed as per the grid codes, and we can definitely discuss maybe parameterization to see if the models can provide that. But there is phase jump power available, uncontrolled phase jump power without a control action. It's there in the models today.
Yeah, maybe thank you, Deepak. Maybe add a little bit comments. I think during normal operation, so during those small phase angle jumps, you probably know other control actions will be activated. But if a phase angle jump is too large, reach the current limits, right? Then you have to have some additional control will be activated to make sure your inverter is not overcurrent. And regarding the model availability, I think those standard library models, I think A1, B1, you can already find them in the PSS latest version of PSSE. C1 model was just approved 2 weeks ago. I guess PSSE and other software vendors will release them very soon. So you probably just find them in the latest tools very soon. Yeah, thank you.
Okay, great. Moving on to the next question, what's the major application of the developed grid forming models from PNNL's perspective?
Okay, so that's a good question. So you can see we are working with WECC for developing those standard library models, because according to the WECC policy, they only accept generic models or standard library models for their interconnection-wide studies. What I mean by interconnection-wide studies, they're studying for the full WECC system. In the PSLF or PSSE, they have 20,000 buses, right? They have to rely on the Phasor models. That's why we develop those models mainly for the interconnection-wide studies. But I believe those standard library models can also be used for some typical interconnection studies, but it's best for the OEM to look at those models to see to what level these models can represent their products, and then they can be used for the interconnection studies too. Definitely, you should also use EMT simulation for your interconnection studies, but I think no one is preventing you from using these standard library models for interconnection studies. Thank you.
Okay. The next one is about what can these models capture. So it's mentioned that positive sequence models can capture dynamics for transient stability, but can it capture the dynamics for frequency stability?
I can take an initial attempt at that. And if I may, I think I'll probably also link it with the next question that talks about conducting small signal studies like eigenvalue analysis, because in my mind, they have some links with each other. Generic models can be used for both of this kind of studies, looking at different kind of oscillatory modes, looking at different eigenvalue analysis techniques, and even getting to understand different stability modes that might exist in the system, but they have to be used cautiously. If they are being used to represent the stability and the modes of a device that is already connected in the network, then the recommendation is it might be beneficial to go back and actually use an OEM model, unless one knows 100% sure that the generic model provides the exact same representation of the dynamic behavior of the OEM's model. But what they can be useful for, in some of the studies that we've looked into, is using the various options available in the generic model, because the generic models have modular structure, they have different kinds of functionality and capability embedded in them. And we can use those various options available with a stability study to actually get better understanding on how performance requirements are to be developed. Like, do you need to have fast frequency response at a particular node or not? Do you need to have grid forming at a particular node of the system or not? Will it help the system if a particular device is grid forming or not at a particular node? Aspects like that, answering questions like that from a planning perspective as one plans the system, generic models are useful for actually conducting small signal studies and frequency stability studies. But however, if it is, as I said, if it's used to represent an actual field connected device, and then attempting to do a stability study with the generic model, one has to be 100% sure that the parameterization represents the behavior to a very large degree of detail.
Yeah, thank you very much, Deepak. I think I just add one more comment, because the asking the eigenvalue analysis, I think the TSAT2 supports the eigen analysis. So yeah, so I'm not sure if the PSSE and PSIF can be used to eigenvalue analysis, but I know TSAT2 can be used for eigenvalue analysis. With those models in those TSAT2, you can use that for eigenvalue analysis.
Okay, so that was the next two questions. Next one is about EMT. So when do we need to do large-scale EMT analysis?
That's just probably if you have different opinion. My opinion is that we hope to better design the inverter control to make sure in the future we avoid doing large-scale EMT simulations, because that is really time-consuming and use a lot of efforts. And my presentation will show that, right, for grid forming, the Phasor models actually can capture the dynamics very well, even compared to the black box EMT model, right? So, but still there is a long way to go. But my goal is try to avoid doing large-scale EMT simulation. That's my own thinking, right?
So I think when do we need to do large-scale EMT will also depend upon what kind of analysis is being done in the EMT. What is the study being done? For example, if there is going to be a control interaction or a subsynchronous oscillation of, let's say, 10 hertz that is going to occur between an HVDC link on one end of the network versus a battery at another end during a contingency situation, then an EMT study will help show that in more detail in addition to screening study. But if the purpose of the EMT study is to do something like getting to know if the frequency nadir is going to hit a different point or not, maybe for that we don't need large-scale EMT study. So I think irrespective, my thought is here, irrespective of the technology that comes in, with having more technology of different OEMs, different control structures, interoperability will become an issue. And then depending upon the contingency in place, there might be scenarios where different devices connected farther away from each other may actually interact with each other through the network. Transmission technologies are going to be coming in with power electronics. The load technologies are coming in with power electronics. So the need to do large-scale EMT analysis is going to be driven by the kind of study to be done, and the various amounts of technology that are there, and that will help determine when one needs to do it.
Great, thank you. I see we are at the top of the hour, so we are going to have to wrap up here. As a reminder for folks, we will be posting the rest, and Wei and Deepak will respond to them, and they'll be posted on the website. Sorry, Wei, did you have something quick you wanted to say before we close
I just saw the next question because I can quickly clarify that, because the question is about whether A1 model, B1 model have an associated plant controller. So our understanding is that the existing WECC plant controller model, REPC, can be connected to REGFM A1 and B1, so we don't have the additional plant controller for A1 and B1. But for C1 model, it's kind of special because it's hybrid control. That's why we have a separate REPC GFM C1 for C1.
Okay, thank you for that clarification. Okay, we appreciate everyone joining. We look forward to seeing you again soon, even perhaps at the October 7th at the next joint GPST ESIG webinar on how AI can tackle the increasing complexity of power system operations. That will be Michael Walsh and Ritesh Madden from gridzero.ai will be hosting that. Further information on all of our webinars and meetings can be found at the ESIG website, www.esig.energy, under events, and in our newsletters and informational emails. Deepak and Wei, thank you again for your time and for the interesting content. We look forward to seeing everyone soon. Thank you.